The first frames show nothing unusual, just a quiet patch of sky where stars sit exactly where they should. Astronomers expected another faint dot, another routine detection, another object passing through the darkness without a story. Then one signal refused to behave. It moved too fast at the wrong angle with a brightness curve that did not match any catalogued visitor. This object was tagged 3I Atlas, a simple name for something that immediately felt wrong. Based on decades of surveys, scientists know how interstellar objects should look. They drift in from predictable directions, slowed by gravity, shaped by long exposure to cosmic radiation. When Oumuamua appeared, it already pushed those limits. It had no clear tail, no obvious outgassing, and a strange acceleration. Many thought that was a once-in-a-lifetime anomaly, but 3I Atlas arrived with tighter constraints, sharper data, and fewer excuses. Its path cut across the solar system like it ignored the usual rules. Telescopes expected a soft curve. Instead, they measured a line that looked almost deliberate. The light it reflected did not fade the way dust or ice normally would. Something about its motion suggested control, or at least resistance, as if space itself was pushing back. At first, researchers assumed an error. Instruments fail. Software glitches happen. A calibration issue could explain everything. Teams reran the numbers, checked the mirrors, compared independent observatories. The signal stayed the same. The object did not slow. It did not wobble. It stayed stubbornly consistent. That consistency is what triggered concern. Nature is messy. Real cosmic debris tumbles, vents gas, and reacts unpredictably. This did not. The more precise the measurements became, the less comfortable the explanation sounded. Scientists expected noise. They found clarity. They expected randomness. They found structure. And when structure appears where chaos should rule, alarms quietly start ringing. Because if the data is correct and the instruments are not lying, then this object is not just another visitor. But something is wrong, and the universe rarely reveals its secrets without demanding a price. The first number that caused silence was speed. 3I Atlas was moving faster than most known interstellar objects at detection, already exceeding escape velocity before entering the inner solar system. This meant it was not captured, not slowed, and not influenced in the way gravity usually demands. Next came trajectory. Instead of aligning with the galactic plane, its path cut across at a steep angle, one rarely seen in natural debris. Objects from other star systems usually arrive along common routes shaped by stellar motion. This one did not. Then there was direction of origin. Backtracking its path did not point cleanly to any nearby star or cluster. The math suggested an origin far older, possibly from a region of space with no clear stellar source. That alone raised eyebrows. Brightness behavior added another layer. As it approached the sun, scientists expected a change in reflectivity. Ice should vaporize. Dust should scatter. Instead, the light curve stayed unusually flat. No tail. No coma. No obvious shedding of material. Rotation was measured next. Subtle changes in reflected light hinted at a slow, stable spin, not the chaotic tumble seen in most small bodies. Stability at that scale is rare without internal structure. Size estimates created more confusion. Depending on reflectivity assumptions, the object appeared either unusually thin or unusually dense. Both options challenged existing formation models. Each data point alone could be explained away. Speed might be extreme luck. Trajectory could be coincidence. Brightness curves can mislead. But together they formed a pattern that refused to dissolve. Teams compared notes across continents. Independent measurements matched within tight margins. Errors were shrinking, not growing. The constraints became tighter, and the mystery deeper. However, the most unsettling detail was acceleration. Tiny deviations suggested a sustained push, not explained by solar radiation pressure alone. The force was weak, but consistent. Natural outgassing could do this, but there was no visible evidence of it. That contradiction split the room. Some argued the models were incomplete. Others whispered that the object was behaving like something designed to travel, not drift. No one said it out loud in official papers, but the implication hung in the air. When data becomes this precise, imagination should shrink. Instead, it expanded. Because precision did not bring comfort. It removed excuses. And with every eliminated explanation, the remaining possibilities grew stranger, darker, and harder to ignore. Imagine a car climbing a steep hill with no engine, no fuel, and no push from behind. It should slow, then roll backward. But instead, it keeps climbing at the same speed. That is the problem 3i Atlas presents. Physics relies on balance. Forces in equal measure produce predictable motion. When an object accelerates, something must be pushing it. For comets, that push comes from gas jets. For asteroids, gravity dominates. For spacecraft, engines burn. 3i Atlas shows acceleration without a visible source. Existing models try to fill the gap. Some suggest exotic ices that sublimate invisibly. Others propose unusual shapes that interact with sunlight in extreme ways. Each model works only if multiple unlikely conditions are true at once. The shape problem is severe. To match the data, the object would need a geometry rarely produced by natural collisions. Long, flat, or hollow structures are unstable over cosmic timescales. They break, erode, or collapse. Yet this object appears intact. Material strength adds another hurdle. Interstellar travel exposes objects to radiation, impacts, and temperature extremes for millions of years. Weak materials do not survive. Strong materials reflect light differently. The observed reflectivity sits awkwardly between known categories. This led to disagreement. One camp argued nature is more creative than humans assume. Another argued that invoking unknown physics is a warning sign. When explanations stack assumptions, confidence drops. However, the biggest issue is probability. The chance of detecting such an object with these properties at this moment is extremely low under standard models. Detection surveys are biased toward common things. Rare things should remain hidden. Yet here it is, clear and measurable. Some scientists suggested selection bias. Maybe surveys are finally good enough to see the weird stuff. That sounds reasonable, until simulations show that even improved instruments should not find something this extreme so soon. Internal emails, later hinted at in conferences, revealed frustration. Not panic, but discomfort. The kind that comes when equations stop behaving. When trusted frameworks start to creak. That's where it gets strange. The more conservative the assumptions became, the less the object fit. Relaxing assumptions helped, but only by stretching physics thin. Tightening them made the object impossible. Science thrives on anomalies, but only when they lead somewhere solid. This anomaly feels different. It does not point clearly to a new particle, a new force, or a simple correction. It points to a gap shaped like intention, though no one wants to say that. However, refusing to say something does not make the shape disappear. It just leaves it unspoken, looming in the background, waiting for braver questions. Theory 1 is the safest. 3i Atlas is natural, boring, and misunderstood. It could be a fragment of an exotic comet, made of unfamiliar ices that do not behave like water. Data support some aspects of this. Interstellar chemistry is diverse. We have limited samples. This theory explains acceleration as outgassing too faint to detect. It explains shape as coincidence. It requires no new physics. But this safety comes at a cost. The model demands materials never observed, shapes rarely formed, and survival through conditions that should destroy them. Each requirement alone is possible. Together, they strain credibility. Theory 2 is rarer but still plausible. The object could be a natural light sail, a thin fragment shaped by extreme forces near a star. Radiation pressure could then provide acceleration. This fits some numbers well. It explains motion without engines. Theory 3 crosses a line. The object could be artificial. Not a probe aimed at Earth, not a message, but debris. A relic of technology from somewhere else. This is speculation, not data. Supporters of this idea point to geometry, stability, and acceleration. Critics point to lack of direct evidence. No signals. No maneuvers. No clear intent. Artificial does not mean active. It could be dead, ancient, forgotten. Mentioning this theory makes people uncomfortable. History shows why. Extraordinary claims demand extraordinary evidence. Right now, evidence is suggestive, not decisive. But something doesn't add up. If the object were artificial, it would explain why it survives, why it moves the way it does, and why it looks the way it does. It would also explain why it does not care about our expectations. Scientists like Avi Loeb argue that dismissing this possibility too early is unscientific. Others argue that embracing it too early is dangerous. Both sides agree on one thing. The data matters more than belief. The ranking matters. Natural explanations come first. Rare natural explanations come second. Artificial explanations come last. That order protects science from fantasy. But it does not erase the tension. As constraints tighten, the safe theories bend. The rare theories wobble. The disturbing theory waits quietly, growing louder only because the others struggle. However, speculation is not conclusion. The object has not spoken. It has not changed course. It has not revealed purpose. All it has done is exist stubbornly in a way that challenges comfort. And sometimes, the most unsettling discoveries are not answers, but mirrors reflecting how small our certainty really is. New observations are already planned. Larger telescopes will track 3i Atlas as long as possible, squeezing every photon for information. Spectroscopy could reveal surface composition. Thermal imaging could expose hidden activity. Future instruments may do more. Space-based observatories could watch without atmospheric noise. Radar experiments might probe structure. Each method adds a piece, not a verdict. Scientists are waiting for change. A shift in brightness. A deviation in path. Any behavior that breaks the current pattern. Consistency has been the enemy so far. Change could be a clue. However, time is limited. The object will leave. Interstellar visitors do not linger. Missed data stays missed forever. The pressure is real. What happens if nothing changes? If the object stays silent, stable, and strange? Science will publish careful papers. Models will adjust. The anomaly will be archived, but the question will remain, because the universe has a way of repeating itself. Oumuamua was once alone. Now it has company. Detection rates are increasing. Surveys are improving. The next object may arrive sooner, closer, clearer. That's where the unease grows. If this is rare, we were unlucky. If it is common, we have been blind. Both options are unsettling. As instruments sharpen, ignorance shrinks. And sometimes what fills that space is not comfort, but wonder mixed with fear. The sky is quiet, but quiet does not mean empty. Subscribe to Cosmic Nexa, because the next discovery could arrive without warning.